Okay, so in this video we will look at how we apply Fourier series into analyzing simple RLC circuit. So quick review of Fourier series. We know that Fourier series is basically a function of ft, and it is a periodic function, okay, a function that is that has a repetitive waveform, and it contains DC component and AC component. All right, DC component and AC component, comprising an infinite series of harmonic sinusoids. Okay, so this is the equation for the series. Take note here, this is n, right? And we also have the fundamental frequency omega naught here, or omega 0, which is 2 pi over t, right? Now this is the basic, or what we have learned from the previous video. So the Fourier series equation is this. This is the general equation for Fourier series. We see here the DC component, and we see here this is the AC component. Now take note, some Fourier series or some waveform may not have DC component, alright, but in general it has both DC and AC. Okay, we also have alternative form, or another way of representing the Fourier series, which is this one. Alright, so this is also Fourier series, but it is based on the amplitude and phase values. Right, so here we can see still has DC component, but here we have capital AN, which is the amplitude, and we have phi n, which is the phase. Alright, so basically we can convert this into this, and we also can convert this into this. Right, how can we convert? The equation is by using this equation. So amplitude AN can be obtained by calculating the square root of AN and BN. Right, AN here, BN here. We square this value, add them both, and then we square root to get the amplitude AN. And then same thing for phi n. We have to get the angle, which means that we have to do inverse tangent BN over AN, and don't forget the negative. Alright, so this is important because we need this in order to analyze the circuit. Okay, in order to analyze the circuit, we have to use Fourier series represented in amplitude phase form. Right, so this is the step of using Fourier series to analyze the circuit. First of all, we have to express or represent the waveform in terms of Fourier series. Okay, express the excitation, in other way the voltage, the current, express the waveform in Fourier series. Okay, ft, and then transform the circuit into frequency domain, because we're going to analyze the circuit in frequency domain, in S domain. And then we have to calculate the output. Okay, output current or voltage current, both in DC and AC components using Fourier series. And then finally add all the components to get the final output. Right. let's look at example. So here we have a waveform. Okay, let's say this is the input voltage or supply voltage of a circuit. So first step is we have to represent this excitation into Fourier series FT here, right? Because we cannot do analysis on the circuit if we only have the waveform, right? The waveform must be represented into Fourier series, into mathematical equation like this. So to do this, we have learned in the previous video, right? Using AN, BN, and A0 to obtain the Fourier series of this circuit. So you can watch that in the previous video, but here in the video we'll skip that process. So basically this is the Fourier series of the waveform, right? So from here we can get the amplitude and phase of the Fourier series, okay, from this equation, right? From this equation. So AN BN, what is AN BN here? AN BN here is, AN BN here is this. So this is the BN here, right? That is BN. BN sine n omega naught t. BN sine n omega naught t. So there is no cos component in this equation, right? There's no cos component in this equation, so there is no AN, only BN sine n omega naught t, right? BN sine n omega naught t. So here this is this thing here, 2 over n pi, that is the BN sine n omega naught t, right? So pi is the omega naught. So BN is 2 over n pi, right? Okay, so BN is 2 over n pi, AN is 0, so the square, the square root, so AN, capital AN, the amplitude is equals to BN, right, which is 2 over n pi. So in this case n is 1, in this case n is 3, in this case is n is 5, and so on, right? Take note that n is equals to 2k minus 1. So when k is 1, n is 1. When k is 2, n is 3. K is 3, n is 5. So means that n only exists odd number value. Okay, n is only odd number. Alright. So from here you can plot the amplitude spectrum, phase spectrum, which we also have covered that in the previous video. Alright. But we need to understand this in order to analyze the circuit. Okay, because we are going to use this value to analyze the circuit. Alright. Now we know that we have the Fourier series. Right. So this is the voltage supply represented in Fourier series. We have 5 ohm, we have 2 Henry inductor. So first step is to get the Fourier series. Second step is to transform the circuit into S domain, which is 5 and 2S. Okay. 2 Henry is 2S in S domain, right? Take note that S here is S equals J omega n, and omega n here is n omega naught. Okay, and omega naught is the fundamental frequency, which is pi, right? Which is pi. Right. So next is so the question is we need to find the V out. We need to find the V out, which is the voltage across the inductor. So to get the V out, we can use voltage divider, right? So this is voltage divider. This is the 2S, all right? The 2S. This is S, and this is the inductor, which is 2, right? And R plus J omega 2, right? J omega is n pi, right? Okay. So using voltage divider formula, V out is basically 2S over 5 plus 2S, right? Times Vs. Okay. So and S is J n omega naught, and omega naught is pi. So S is J n pi. Okay, S is J n pi. S is J n pi. J n pi. Right. So this is the equation for V out. Right. Next is we have to look the V out in AC and DC component. All right, because Vs has DC and AC component, so V out also has a DC and AC component. So what is V out if Vs is DC component? So we know that in DC component there is no omega n, or n is 0, so we can replace this with 0 with 0, so we get V out is 0 volt. Right, in this case there is no DC component of the output, for the output. Alright, take note here, this is Vs, so this is Vs, which is 1 over 2. So for voltage supply, the Vs has DC component. However, when we calculate for V out, there is no DC component. Okay, so this is DC component of the Vs. However, when we do the calculation, there is no V out. There is no V out for DC component. Alright, so that is the for DC component. Let's look at the AC component. So for AC component, now this is the equation again, V out. Alright, voltage divider. Okay, now what is Vs here? In this case, Vs is 1 over 2. Now for AC, Vs is, we represent it in amplitude and phase form, which is 2 over n pi with angle or phase negative 90 degree. So how can we get this? From the an and phi n, the amplitude and angle. Alright, so this is the Vs represented in amplitude and phase. Right, so this is the Vs. And now since this is in phasor form, so we have to convert this into, from rectangular form into phasor form. Okay, convert this into phasor form, rectangular form into phasor form, because we want to combine with the phasor form of the Vs. Now here we can see that 90 degree we can plus with negative 90 degree, which is 0, and then we minus this value, which is this negative tan inverse tan. and then 2n pi, we multiply with 2 over n pi, and then we divide it with this, so we will get this, right? So this is the an, and this is the angle phi n. Then we put it back in the Fourier series in time domain ft, or ft of v out t, right? We'll get in a0, which is 0 actually, which is 0, and then an phi n, which is this and this. Alright, so this is the v out in time domain. Okay, we have the an, capital An, and then we have the phi n, and of course we can also represent it in the typical form of the Fourier series, which is a cos n b sine. So here we can get that if we calculate first three terms, which is k 1, 2, 3, or n equals 1, 3, 5. Okay, if k is 1, 2, 3, n is 1, 3, 5. So first three terms we calculate will give us this. This is the amplitude for first harmonics. This is the amplitude for third harmonic, right? Third harmonic, and then this is the amplitude for the fifth harmonic, or the third component, or the third terms, and the angle as well. And this is continue until infinity. All right. And then finally, once we if we can get the v out of the circuit, we can also do the same process. Okay, we can do the same process to get the current as well. Okay, depends on the question. If the question asks you to calculate the voltage, use the voltage equation, and if the question asks you to calculate for the current, you can use the current equation. And then finally we can also get the total average power. Alright, total average power, which is based on basically VDC times IDC, and then 1 over 2 times summation of VNIN cos theta n minus phi n. So theta n is the angle for the voltage, phi n is the angle for the current. Okay, so basically we can also do the same using the same circuit to get the power as well. In this case, for example, we are calculating the V out, so we can also do the same thing to calculate the V I out, or I through the inductor, and also by multiplying VDC IDC plus 1 over 2 summation of V and IN cos of minus these two angle voltage angle and current angle, we can get the power of the average power of the inductor. Okay, using this equation. Okay, thank you.